Hello, game theorists. Welcome back to our very last episode of Game Theory. We're looking at our practice session today. So by now you have finished all the problems. Next step, we go over the answers together. We'll start in the short answer section. Number one asks you, what does BATNA mean? And what does the acronym stand for? So what BATNA stands for is best alternative to a negotiated agreement. The idea is that this represents what each player could get if no deal is reached. So the example I kept using was with my negotiations with Binghamton University. So I had the job offer back in summer of 2019, and I was weighing that option against staying at Truman State. So if my seller negotiations failed to reach a deal, my outside option was staying at Truman State. And how much money I could have gotten there was my BATNA. So that's number one. It's a very important idea in bargaining to know what's the other side, to use what's the other side's BATNA. I almost said to know the other side's BATNA. One difficulty is that when negotiations happen in real life, we often don't know the other side's BATNA. That's a complication. Alright, moving on to number two, we had the alternating offers model in our bargaining chapter. One of those models had impatience in it. I said that it's an advantage to be able to make the first offer, and here we'll explain why is that true. So the way these alternating offers models work is that each time that no deal is reached, the surplus diminishes. That's going to make both players eager to reach a deal. So as a result, you can make the deal in your favor and propose a deal in your favor because the other side wants to get a deal quickly. They don't want to see the surplus fall. They can still accept a deal that is biased in your favor. We also saw some numerical examples of that in the bargaining chapter. So that wraps up number two. Moving on, we have number three, the last one in the short answer section. So here looking at the Vickrey auction, we had an in-class game like this one. The way it works is that highest bid wins, but you pay the second highest bid. I showed in our videos that bidding your value is weakly dominant over bidding above and below your value. Here we'll explore why it's better than underbidding. So we'll look at 3 cases. So if the highest bid out there is in excess of 20, then it doesn't matter. So you lose the auction whether you bid 20 or whether you bid 19. Someone else beat you. Another possibility is what the highest bid from your other bidders is below 19. So it could be like a bid of, let's say, just to pick a number, 15. Well, in that case, whether you bid 19 or whether you bid 20, you're going to win the auction. So again, it doesn't matter. Now, remember here, unlike a traditional auction, you don't pay what you bid. Rather, you pay what the second highest bid is. So you pay 15. So your payoff is the value of the object. You said the object is worth 20 in your view, minus what you paid for it. Either way, you pay 15, so you have 5. So what we've established so far is that in these first 2 cases, it doesn't matter if you bid 20 or if you bid 19. Either one gives the same outcome. However, there is one other case we have not explored yet. Let's talk about case 3. Spoiler alert, in this case, it does matter if you bid 20 or 19. So you talked about what the highest bid is above 20. We've talked about the highest bid is below 19. So last possibility, what if it's bigger than 19 and smaller than 20? So I said bids can include fractions, so that would be, let's just pick 19.5. So if you had bid 20, you would have won the auction. So you get the value of the object, which you think is 20, minus the second highest bid, 19.5. So once again, in this special kind of auction, you don't pay what you bid, you pay the second highest bid. We said second highest bid was 19.5. So what you get on net is 20 minus 19.5, and that comes out to 0.5. Now, if you had bid 19 instead, you lose the auction. A bid of 19 loses to a bid of 19.5. As a result, your payoff is going to be 0. You don't get anything, but then you don't pay anything either. So what does this mean? Well, a bid of 20 in this case gives us a higher payoff than the bid of 19. So if it doesn't matter in case 1 and case 2, but bidding 20 is better than in case 3, that means that overall it's better to bid 20. Bidding 20 is always going to be at least as good, sometimes better than bidding 19. And that wraps up number 3. Moving on, let's talk about the problem section. So problem number 1, we have our alternating offers model. Once again, the surplus is diminishing. V is going to be 50. And each time we don't reach an agreement, the surplus goes down, falls by 15 in round 1, and falls by 9 in round 2, and 16 in round 3. So as I said, one important consideration is what is everybody's BATNA? So what could they get if no deal is reached? So let's say there are 2 players, Jason and Matt. This is based on one of my office mates from grad school, back when I was at the University of Oregon. So Jason's bet, let's say his is 6 and mine is 4. I get to make the first offer. Now this question here, you see, talks about the distinction I made in the videos and I emphasized. Always be clear about, are we talking about the total value each player receives, or are we talking about how much of the surplus each player receives? They're not the same thing. So let's tackle part A. So first we'll calculate the initial surplus. So total value is 50. And then we got to subtract off each player's BATNAs. So Jason's BATNA is 6 and my BATNA is 4. So that comes out to 40. We know we can solve these games by using rollback. It's a sequential game. So we know round 3 is going to be the final round. So you have the initial surplus of 40, but then we also have the surplus, the loss of surplus from the first 2 rounds of failed negotiations. So because no deal was reached in round 1, surplus went down by 15. Because no deal was reached in round 2, surplus had gone down by another 9. So that comes out to 16. We also know that if the deal suggested in round 3 is rejected, the surplus will go down by another 16. So that's going to leave us with nothing left. I keep making mistakes with the 0 and 9 keys. I'm not a great typist. Alright, anyways, back to the question. So Matt makes the first offer, so I offer in round 1. That means that Jason offers in round 2. That means that I offer in round 3. We take turns. So I get to make the offer. I know that if my offer is rejected, then there'll be no surplus left. So that means that Jason will get 0 if he says no. So I can offer Jason 0, and he has no reason to reject me. So if Jason gets 0, that means there's 16 left over for me. This is of the surplus. So the usual objection, I talked about this briefly in the videos, but I'll just restate it here for some extra review. So it's a valid point that if I make this offer, Jason is indifferent between saying yes and getting 0 and saying no and also getting 0. However, to be in equilibrium, it just has to be the case that doing something different, saying no, can't be strictly better. If saying no is equal, then we still have an equilibrium. If you want to do this in real life, I suggest give Jason a penny so he's not literally indifferent to make sure he says yes, but it's still an equilibrium where he gets 0. So it makes life a little bit easier for the calculations. We don't have to keep track of extra pennies floating around in each round. So stick with I get 0, Jason gets 16. Sorry, I get 16, Jason gets 0. I said that wrong. Typed it out correctly though. Alright, so that's round 3. So now rollback means we go back to the previous round and we figure out what happens there. The surplus going into that round is, we have 40 minus 15 because the original surplus was 40. Because round 1 didn't work out, it went down by, where did I write it? Went down by 15. So it says Matt makes the first offer over here. That means Jason makes the second offer. We established that I can secure 16 for myself by saying no and by making the offer in round 3. So to make sure I say yes, you have to offer me 16 or more right now. So to save as much as possible for himself, he offers me just 16. So the total is 25 of surplus, and I'm getting 16. That means there's 9 left over for Jason. This is, again, of the surplus. And once again, you could toss me an extra penny, make it 16.01 to make sure I'm not indifferent, but it's still an equilibrium where I say yes to 16.00. Alright, round 1. So at the beginning of the game, so we know at the beginning surplus is 40. Whoops, 40. Initial surplus is 40. And it says Matt makes the first offer. We know Jason can secure a payoff of 9 if the game goes on. So I offered Jason 9 in the first round. That means there is 40 minus 9, which is 31, all for me. So that's how the surplus is divided. So again, be clear about, are we talking about the surplus or talking about the total amount? So the surplus, Matt gets 31, and Jason gets 9. For the total amount, you add in the BATNAs again. Each player has to get at least their BATNA to make sure they don't do the outside option. They don't just go work independently. So my BATNA was 4. So I get 31 plus 4 overall, which is 35. Jason's BATNA was 6. So he gets 9 of the surplus and 6 from his BATNA. That comes out to 15. I mentioned in the video that one way to check yourself is that the total amounts sum to the original value. So here we have 35 and 15. We start with a total value of 50. 35 plus 15 equals 50, so that sounds right. Alright, so that's part A. Moving on to part B. Now we're looking at what if Jason makes the first offer. It's a shortcut here. That shortcut is called our friend symmetry. Let me put this in different colors so we're clear about what's the answer and what's the question. So, to be clear though, with these kind of questions, you can appeal to symmetry for a division of the surplus. You can't do that for the total amount. Total amount depends upon BATNAs. BATNAs might not be symmetric, and BATNAs in this case aren't symmetric. So in part A, I got 31 of the surplus, and Jason got 9. However, now Jason makes the first offer, not me, so it's going to be flipped. Now to find the total amounts, we add in each side's BATNA. So Jason gets his 31 plus his BATNA of 6. Jason's BATNA is 6. So 37. I get my 9 of the surplus, and I also get my BATNA of 4. So I got 13 overall. And again, you can double check yourself. The total amounts, 37 plus 13, should sum to the total value. 37 plus 13 equals 50, so that sounds right. Alright, part C. We add a third player to our story. Our examples in the videos had just 2 players, but the same logic, the same rollback approach works to 3 players. Allison has BATNA of 0. We'll assume that Matt and Jason have the same BATNAs as before. I make the first offer, Allison makes the second offer, and Jason the third offer. So we know from before that the surplus in round 3 is 16. We established that over here in part A. And we also know it's going to vanish entirely if no deal is reached. and we know that Jason makes the third offer. So he's in round 3. So because everyone gets 0 if they say no, that means everyone here is really, really desperate for a deal. Jason, who's making the offer, can exploit that. So he keeps all 16 for himself. And we're stuck with 0. We have no incentive to say no because we'll get 0 anyways. Again, Jason could toss us a penny and say I get $15.98, and you guys both get 1 cent to make sure we're not indifferent, but it's still an equilibrium where we say yes to 0, so don't worry about those spare pennies. We roll back to round 2. We know from earlier that in round 2, the surplus is 25. We know that Allison makes the second offer, so Allison is the one making the proposal. By the way, Allison is another one of my office mates from the grad school days at the University of Oregon. So Allison's done her rollback reasoning. She knows that if no deal is reached, then Jason's going to get himself 16 in round 3. I can't get anything, so she doesn't have to offer me anything. She gives Jason his 16, so he'll say yes. I can't get anything, so she doesn't have to offer me anything at all. The surplus is 25, and Jason's getting 16 of that. She can keep 9 for herself. We know in round 1, the surplus will start out at being 40. I get to make the offer. It says Matt makes the first offer over here. So Jason can get 16 for himself if he says no. And Allison get 9 by saying no. So make sure I say yes. I give them that offer right now and keep the remainder for myself. So 16 and 9 is 25. Surplus is 40. 40 minus 25 is 15. And they'll say yes because they have no better alternative. So that's how much of the surplus we divide. So that's the answer for the surplus part of the question. Total amounts. We now consider the BATNAs. So I get my 15 of the surplus, and I also get my BATNA. My BATNA is 4. Means I get 19. So Jason got 16 of the surplus. He also gets his BATNA. His BATNA is 6. Allison gets 9 of the surplus. She also gets her BATNA. Allison's BATNA is 0. So those are the total amounts. So because Allison's BATNA was so low, her outside option was nothing, that weakened her bargaining power and lowered her total amount that she received. That's the intuition for what's going on here. Alright, moving on. Our very last problem in our very last video. Problem number 2. So here's an evolutionary game. We have 2 species. So the first one comes in either A types or B types. The other species can be X or Y types. So I realize these problems with different species can be rather lengthy, so I did some work for you guys to keep this short and tractable. Let's assume you already did a bunch of math already and you already found this polymorphism. So there will be 2/3 A types and 3/4 X types. So PA is a fraction of A types, PX is a fraction of X types. So as you can imagine with an online exam, it's going to be tricky to draw diagrams. I might do something like this where I've drawn some diagrams for you already. You got to pick which one is appropriate. But it's still good to be able to draw the diagrams on your own to do some of the analysis. In part C, you'll be drawing a diagram on your own to answer the question, though of course I can't make you draw it online, but it will help you with the reasoning to find the right answer. Okay, so let's say that the A types are fitter if and only if P of X is above 3/4. So which diagram is consistent with that? So if Px is above 3/4, where is that on our diagrams? I put Px on the x-axis. So being above 3/4 would be in this part over here. So we're saying that the A types are fitter when you're in this region. If that's true, then you'll start seeing more A types. If A types are fitter, they'll live longer, they'll reproduce more, they'll pass on their genes, so PA is going to go up. Well, PA is on this axis over here, so if you're in this region, PA is going to rise, so the arrow should be pointing up over here. Now, as you can see in this diagram number 1 over here, that's not happening. The arrows are pointing left and right. They should be pointing up. So that rules out number 1. How about number 2? That looks right. So we said when Px is high, then A types are fitter. So the arrows will push you upwards for PA, and that is indeed happening in diagram number 2. Let's check the other side. This happens if and only if Px is high. That means that if Px were low, like if Px were just 0.1, then the B types would be fitter. So when Px is lower over here, and if B types are fitter, that means PA is going down, so arrows should be following this region. That is indeed happening, so that means number 2 is correct. Alright, that's part A. Moving on to part B. So same setup. Now we're looking at the other part of it. Let's say that X types are fitter than Y types if, and only if, P of A is small. So which region of the graphs corresponds to PA being below 2/3? PA is on this axis, so here's when PA is high, getting close to 1. Here's where PA is low, getting close to 0. So PA being low is down here. Now we're saying that when PA is low, which we are when we're in this region, then the X types are more fit. That means you'll start seeing more X types. So that means the arrows will be pointing to the right. Well, in this diagram here, the arrows are pointing to the left. That can't be right. So it's not number 1. We said arrows should be pointing to the right in this region, and they're pointing up and down, so number 2 can't be right. Number 3 is also pointing up and down, which should be pointing left and right, so you can rule out number 3. Last possibility, what about diagram number 4? So that's saying when PA is low, then PX rises. Over here he said, when PA is low, PX rises. So that's right so far. To be thorough, let's check the top part as well. So this says when PA is high, when PA is getting close to 1, then PX should fall. Is that right? So this is true if and only if PA is low. That means that if PA were high, then the Y types would be fitter. So high PA means more Y types. More Y types means fewer X types. That means that PX should fall if PA is big. And here, PX does fall when PA is big. So diagram 4 is correct. So that's part B. Now for part C, we have to combine our conclusions from A and B and find a stable equilibrium. So I'm not asking you to upload your diagram because you can't really do that if you're typing things up. I do, however, want to show you the diagram so you can see the reasoning behind how you get your answer. I'm not sure how to draw a diagram on a computer either, so, well, I could do it. It'll be very slow. I'm going to switch over to pencil and paper and show you how to do that.
Hello, game theorists. We are in the very last part of the very last problem of our very last episode. So we're doing this evolutionary game, and we're trying to find which equilibria were stable, and we're trying to draw a diagram. We established earlier that diagram 2 was consistent with this fact. We also established that diagram 4 was consistent with that fact. So we want to combine both these together to make one diagram and then analyze stability. So here's what that would look like. So here is PA, and here is PX. So diagram 2 is telling us the arrows are going down in these regions, and they're going up in these regions. Diagram 4 tells us that the arrows are going this way and this way up here. They go in the other direction down there. So that's how you combine diagrams. So for stability, I said what you do is you check the four corners and you also check the middle. You don't worry about these edges here because those are never stable. And they're not even equilibria. I don't think. All right, so to look at stability for each one, you follow the arrows. So we start over here where PA and PX are both 0. If we were to deviate a little bit from that equilibrium, the arrows are going to push us away. So it pushes in this direction. So that's not stable. Well, this one here, what if we have PA still being 0, but now PX is 1? Same procedure, follow the arrows. So the arrows here are going to push us up and to the right. So they push us up though, it's going to take us further and further away. So that's also unstable. This corner here corresponds to both PA and PX being 1. Is that stable? So we deviate a little bit. This arrow is going to take us away. It's going to push us back up, but it's also going to push us in this direction. So that takes us further away. That's unstable. Then there's PA being 1 and PX being 0. You start there and deviate a little bit. This arrow pushes you back, but the other one pushes you down, so overall it's going to take you away. We also have to check the one in the middle, so that's PX. Oh, I think I put PA first typically, so let's be consistent. Doesn't really matter if it's PA first or PX first. So in the center, if we start deviating from that, if we go out, say, over here, the arrows push us away, so that's also unstable. If you check any other directions as well, I think you get the same results. If you go here, arrows push you away, go there, arrows push you away, go there, arrows push you away, so it's unstable. Now, it's sufficient to show that's unstable in just one direction to show that's unstable overall. So it looks like this game has no evolutionary stable strategy. If you follow the arrows here, it looks like you kind of go in some sort of circle. Well, ESSs are not guaranteed to exist. We do know that Nash equilibria exist in general. I showed a sketch of the proof of that way back long ago. ESSs, though, that is evolutionary stable strategies, are a subset of Nash equilibria. We said all stable strategies are Nash, but not all Nash equilibria are stable. So while there's always a Nash equilibrium, we're not assured there's always a stable evolutionary equilibrium. So this is not a mistake. All 5 equilibria really are unstable in this game. All right, that wraps up our show, and that wraps up our course. So, best of luck on the final. Stay safe and stay healthy.